Recording. So welcome everybody to our second seminar this summer term in our Gamma seminar. So today we have the pleasure to guest Roman Popovych from the Silesian University in Opava, the Czech Republic, and the Institute of Mathematics of Ukraine, of National NES. Roman,
National Academy of Science.
Of course, National Academy of Science, Ukraine, Kyiv. So, Roman, thank you very much for accepting our invitation. It's a pleasure to have you here. So, please, the floor is yours.
Thank you very
all here.
Thank you very much for the introducing and also for invitation to talk on this seminar. For information about the series of seminars I received from Sergei Artur. Artur Sergeyev, and I'm happy to participate in this seminar. And I already listened several issues of this seminar, and it was very interesting for me. Okay, the subject of my today talk was suggested by Javier, and it's the basic, in fact, for this talk. And the title of the talk is Realization of Lie algebras on the line and new group classification on 1 + 1 dimensional generalized Klein-Gordon equation. Yeah. So as I told, so it's one basic paper which was published several years ago, but in fact the related tools which we use to classify this class of equation was developed in a number of papers with my collaborators and my pupils, and at least two of them are basic. Yeah, this is like initial development of the theory, and this is already more in which essentially involves the language, at least, of groupoid theory. What mean group classification of a class of differential equations? So first of, I will formulate this definition rigorously, but just to introduce them at once. So suppose that we have a collection of systems of differential equations. Of course, we have not just arbitrary collection, but with special property. Of course, number of variables independent should be the same, number of dependent variables should be the same, but also there are additional restrictions for a class of differential equations. And then we would like to classify symmetries of equations from this class, or system of equations from this class. What does it mean? Of course, there are different kinds of symmetries. Simplest one are Lie-symmetries, which are somehow continuous point symmetries. But there is also discrete point symmetries. There are contact symmetries, different kinds of generalized symmetries, and so on. But we will talk about classification of Lie-symmetry, and or we also can classify contact Lie-symmetries, but only for these two classes. In fact, the classification problem is well posed in classes of differential equations. So, and then we will classify for a system of a differential equation from a class L, those cases where maximal Lie invariance algebra G theta is wider than such algebra for a general situation or general system in this class here. And it is necessary to classify up to appropriate equivalence related to point transformation between such systems. And to solve group classification problems, so we should find all values of this parameter in the systems, theta, which we will call arbitrary elements, for which this specific algebra, G theta, is wider than this general position algebra. And for rigorous formulation group classification problem, of course, we should clearly understand what is class of differential equation, which equivalence use, what invariance algebra we consider as common or general, yeah, and in which sense this algebra is common or general. But we will see the very nice class of differential equation. I will not talk about all possible variants in these definitions, correct reformulations, and so on. What is past of group classification theory? Of course, if we talk about Lie-symmetry, so we cannot avoid to mention that all these things in fact was initiated, initially studied, and the initial theoretical background was developed by Solutsi. And he also solved first group classification problems, and I listed this. So he classified ordinary differential equations. It's in fact was initial problem for Solutsi because he tried to describe integrability of solvability of ordinary differential equations in terms of symmetries. Yeah. Of course, he did not reach completely his aim, but he did group classification of ordinary differential equations and especially second order ordinary differential equations. And then many people, more than 100 years, tried to complete different pieces what Lie left unsolved in this classification. He also considered group classification of second order linear partial differential equations with two independent variables. And this classification was done over the complex number and over the real number. I don't know, maybe there is some complements, but I'm not sure that there is complete classification well written over real numbers. And the last classification is directly related to the subject of the today talk, because it was also somehow stimulated by this work of Lie to classify this class of equation. Lie classified nonlinear Klein-Gordon equations, which of this form, so they in light cone variables, u x y equal to f of u. So Lie really classifies. So there are not too many interesting cases. Of course, there are linear equation, Klein-Gordon equations, or wave equation. And if we talk about, they definitely have wider Lie-symmetries than nonlinear equations. But if you talk about nonlinear equations, so we have only two kinds of nonlinearity. It's exponential function, and so it becomes Liouville equation. It also has infinite algebra of symmetries and power functions, so power of u. And Lie wrote that it would be interesting also to make classification of this generalized class where right-hand side depends not only on u, but also on the independent variables. And this class equations was considered by Lagno in 2005 when they classify a much more general class of differential equations. It was like one of the cases which should be considered separately. They consider the first point that they consider not light cone variable that usual D'Alembert, and then on the they also involve then derivative with respect to space variable. But the first point that their proof in fact contain gaps, so they did not prove that in required cases the algebra of symmetries is infinite dimensional, but their proof was based on this fact. And second point that there are some mistakes in this classification, so that's why it was big progress in this problem, but it was not the final solution. And that's why we decided to consider this problem, and jointly with my colleagues, Boyko and Lakazyuk, we solved this in 2021, this problem.
Sorry, just one question. Big or small problems? Because in my experience, all these classification problems, they always have some kind of lack of some particular cases? Is that these problems were big ones, or was it a kind of, that something is missing?
Yeah, so it seems to me one case, it seems to me, was missed, and there are several incorrectnesses just in cases, yeah. And so some degrees were not too correct and so on. Yeah. And as I said, so it was more or less okay, yeah. But since the proof was not complete, yeah, somehow, and also it was classification was not itself was not ideal. So we decided to do this precisely. Yeah, this problem.
Well, it's a good idea. There are many of these problems, classification problems, that it turned out that works summing up and correcting mistakes turned out to be very important. I remember one example with classification of Lie algebras of vector fields on the plane by Lie.
Yes,
That
yes,
is a
yes.
completely miss. It's a mess. At 13 points, it's very good, of course. But then Oliver, Artemio, Ikamran
Mhm.
corrected it. And Winter wasn't sure that it was okay, but never said why.
Uh, so you see, but over complex field, the classification is completely correct by Lee. Yeah. So Oliver, Kamran, and Gonzalez Lopez, they corrected only over real field, and they find only one class of algebras which Lee missed occasionally. Yeah, but at the same time, yeah, they rederive this classification, and now we have really like justified and trustable result. Yeah, even over real field. For
Yeah.
example, about classification of Lie algebras for three or in the space, yeah, when we have three coordinates, yeah, vector field, then situation is much worse, yeah. Do you know
I
about this
know because I
classification?
have some results on it. I mean,
Yeah.
it's crazy. It's
We,
really hard.
yeah, because this classification was started by Sophus Lee, and he considered some classes of realizations by vector fields of Lie algebras. And then it was huge paper by Amaldi. It's like maybe in the beginning of 20th century, maybe. And then, yeah, a number of then people tried to complete this classification. For example, it was series of papers by Hilgarten about this. So, but you see, it is still problem that somehow it is necessary to make realization in canonical way for them to be easy to compare. Yeah. And even in classification of Lie algebra, we also know such situation when for seven-dimensional nilpotent Lie algebra. So completely trustable and correct classification exists only up to dimension 6. And in dimension 7, maybe already classification, but I'm not sure about where exist dotsons classifications here. And but at least 10, yeah, such different classification exist, and they're very difficult to be compared. And people always make fighting and discussion about whose classification is correct and whose contains some mistakes. Yeah, it's really a problem, yes.
Yeah,
But
a big one.
at the same time, so we try to develop methods, yeah, which are the first point systematic, yeah. They are more or less easy to compute, and it is easy also to check. And then it is not of course we can also make misprint some mistakes, but then it is very easy to check where we make a mistake, and so it is very easy. Somebody can correct if he will find some weaknesses. But I will talk about this in the context of group classification, maybe a bit more, maybe on next slide. Yeah.
Okay,
Okay.
okay. Just one comment that indeed what you said that you have new methods to obtain it and to understand the problem and to check whether it's proper or not. In my opinion, sometimes it's more interesting even the classification itself. And at a certain extent, this is a very good thing.
Yeah. But I at once should say, yes, that in fact, yeah, what we do is just development of methods of Sophus-Lie, and nobody, in fact, pay attention to this too much. But it's always happened, yes, that in fact, it's like with Noether paper that people did not understand, especially physicists, Noether result about the connection between symmetries and conservation law is the most generality, yeah. And then they derive, in fact, some particular result here for which, in fact, contained in results of Noether. Yeah, and they always state, "Oh, we generalize Noether." Yeah, here the situation not the same but similar. Yeah, so in fact, for example, method which we apply, algebraic method of group classification, it is basic method for this class of differential equations, for ordinary differential equation. What is the idea? That okay, we have two variables, yeah, and we can consider the group of all local pseudo group of all local diffeomorphisms. Corresponding algebras will be just the realization of Lie algebras by vector fields on the plane here. And since we know that Lie algebra of the Lie-symmetry algebra of ordinary differential equation is finite, that then we can classify all possible finite dimensional realization of Lie algebras by vector fields on the plane, and just then construct equation which admits its algebras and check whether they maximal or not. This is the main idea which was presented in the work by Lie, but then it should be generalized somehow to understand to which situation it can be applied, because for ordinary differential equation we consider the entire group of local diffeomorphisms. But if we have narrower class, so it's already too wide group. But in which situation then this method works properly? Yeah, we should understand. And I will make groupoid for the class of differential equation. But just a week ago, I found that Sophus-Lie computed equivalence groupoid for this when he classified this differential equation, second order linear PDEs with two independent variables. So yeah, this is why I cannot say that we invented all from very scratch, but we just developed what was done by Lie, but in proper manner with modern terminology. Okay, and then in the history was big gap in time when this theory stopped to develop it, but it was renewed by Ovsyannikov in fact in the end of 50s and start to quickly develop it, and was suggested different notions, different methods. For example, here it was already again close to computing equivalence groupoid of the class of differential equation, the work by Kingston and Sophocleous. And then two groups, Winternis with his pupils and collaborator, start to compute something like equivalence groupoid and apply algebraic technique to group classification of differential equation. And it was also a big flow of Zhdanov and Lagno and their collaborator when he applied in a bit different way than Winternis and Gagnon algebraic technique to group classification. But if we will characterize situation, this group classification problem in general, yeah, we discussed it already with Javier, yes, that in fact there are many papers here with non-rigorous and precise definitions, yeah, including the most basic one. Sometimes problems are not properly posed. It is not clear what the arbitrary element, which conditions really satisfy. So even class of differential equations to be classified is not described precisely. Yeah, and this is already strict statement that most classification presented in literature are not completely correct, and it is not like it's happened that mistakes happen, but the problem is many of them are essentially incorrect. So people in principle made incorrect classification. As example, it's for statistic, I reviewed one paper, and before revision, a classification of this paper, classification table takes 3 pages and 68 cases, and they were very cumbersome. So with huge nonlinearity, very complicated algebras, and so on. And after this result was criticized, so volume of the table was reduced to 1/4 of the page, and 16 cases very, very simple cases. Yeah, this is why, yeah, situation is really not good with classification problems in this sense. And the most commonly used method of classification is just a brute force approach. So people derive system of determining equations for Lie-symmetry and try to solve them somehow. And under this approach, often proofs are not included in the paper, and it's even not possible to check. Where it is sometimes, of course, mistakes are evident. Yeah, but if, for example, there's not so evident that even it is not possible to check this classification whether it's correct or not. Yeah, so this is a problem. That's why we decided to revise this framework. Yeah, and it is necessary to answer a number of questions when we. Of course, it is again not final formalization, and many of formalism already don't like. Were not liked by colleagues because they started to talk, okay, why we need to introduce groupoids in the theory of group classification. Yeah, but it's really necessary. Yeah, and it is necessary to further generalize this notion and maybe make them more formally, but at the same time we should preserve balance between mathematical formalism, yeah, and in fact it's quite applied field. Yeah, that's why it is necessary to find such balance, not to make it too formal. So what are questions? So the first of all, we should answer the question, what is a system of differential equation? But I will avoid this question in this talk. But more interesting for us is what is class of system of differential equation, what is its subclass, what we consider as a point transformation within the class, and then corresponding object to involve in equivalence of systems and within the class equivalence group, equivalence groupoid, and so on. Then we should correctly pose the classification problem, and then to properly solve them, to apply adequate method, we should know how to characterize classes of differential equation, how we choose nice classes of differential equation, or how we can change a given class of differential equation to make it nice. And here also will exist a number of different approaches.
Just a quick comment, if I may, because last week we have Rui Loya here, Fernandez, and he has a work with a PhD student of his that will be in Cornell, I think, this year, that they describe every partial differential equation, everyone, in terms of something called a Lie algebraic, and it can be described by means of related, some structure by means of a groupoid related to it. And the approach was, well, we were studying this approach while being here, and it's an approach that it is made for equivalence problems, classifying the Cartan problem for different structures. So really, in something like a week, we found methods that were not able to be described by means of jet manifolds and things like that for something like a couple, 20 or 30 years. So maybe it's a good thing to take a look. Yes, it's a comment because it's a method to use algebraic methods, and it seems to be quite promising.
Yeah, because up to now I don't know how to involve algebra in what I do. Yeah. So, and
It's
if you will, please send me, Javier. Yeah, I will be very
yeah, sure.
appreciative.
And if you need anything, you can ask me because I hope I will work with them since it's
But
quite interesting. Let's see.
do you have some links or text or whatever on this subject?
I will send you a link. Sure.
Okay. Thank you. Okay. So, what is class of differential equations here? So we have some how differential function here, but structure of this differential function is not just depends on jet variables, but also it depends on some parameters. Yeah, it may be function, it's differential function themselves, or in constant, for example. Yes, sometimes happen if it is big system of differential equation auxiliary for them. Okay, and yeah, so we have independent variable, we have dependent variable, and this I'm sorry. No. Ага, добре, дякую. Okay, sorry. Then, yeah, but in addition to this form, yeah, we also have auxiliary system of equation, or sometimes even various inequalities, which should satisfy these arbitrary elements. Yeah, and we have set of solution for this equation and inequalities, and we call the set of system of differential equations where arbitrary elements run through the set of solution of this auxiliary system, the class of differential equations. Of course, maybe it's already time to reformulate all this in terms of shift theory, and corresponding pseudo group and so on, but still we use this light language to describe the class of differential equation. But in any case, even this is a progress, because, for example, even in work of Ovsyannikov and then his successor and further, so in definition of class of differential equation, used only arbitrary elements without its possibility of differentiate them, but it is essential. And also, usually, it was not paid too much attention to these auxiliary equations and auxiliary inequalities. So when somebody writes a class of differential equations, so they usually write only this form, but without this all auxiliary conditions. So, and the class of differential equations, we have different jet spaces. So, of course, we have basic space of independent variables. Then we have this jet space, appropriate order over this foliated space. But then we should attach to the space a tuple of arbitrary elements. So it's already extended space by coordinate cells of arbitrary elements. And sorry. Okay. Then we should consider jet space where over this foliated space. Yeah. So whereas jets itself plays the role of independent variables. And then we should also take into account both orders which are in form of the system of differential equations and also jets. Okay, what are some classical examples of simple classes of differential equations? So we consider nonlinear diffusion equation. Diffusion nonlinear is in quotes because sometimes even linear equations where this constant Heat equation included in this class for completeness. Yeah, so we have only one arbitrary element. This is D, which depends on U, Of course, if we extend, so then this form, so we will have derivatives of d with respect to u as arbitrary element here. And then, yeah, but so once more in this form, yes, so it can be not only arbitrary elements, but also their derivatives with respect to the arguments. We consider as basic as second order jet space, we have one arbitrary element. In general, then we should consider that arbitrary element depends on all second order jet variables up to second order. Yeah, but since it depends only on u, then we have such system of auxiliary equation. And we definitely have auxiliary inequality. At least d should be non-zero, because then if d is 0, we have the generated equation ut equal to 0, yeah, which should be excluded from this class. But maybe we also should add equations that d depends on u, because then equation becomes really nonlinear. So the second class is the same way in linear filtration equation, where we have that f depends on derivative of ux with respect to x, and the same just second order jet space. Sorry, here misprint. And then, yeah, we have auxiliary conditions that f does not depend on other jet variables, yeah, and natural inequalities that f is not equal to 0. But again, to have nonlinear filtration equation, we should add conditions that f with derivative of f with respect to ex is non-zero. It's a bit more complicated class, nonlinear wave equation from elasticity theory. It's strange combination of dependence on x and ux, not on other variables. And nonlinear, so yeah, it's similar things. But for example, if we would like to consider nonlinear equation, so it's already we have such inequality for description. So classes which was considered by Stufus-Lie, yeah, we can describe in the same way. So we have here arbitrary element f, which depends on all jet variables up to the p-1 derivatives. Yeah, this is linear equation. Of course, for second order linear partial differential equation, we should have conditions that these coefficients of second order derivative don't vanish. Yeah, and this is class related to our talks, as we already discussed it, in linear wave equations. So what a point transformation in classes of differential equations, what algebraic structures are related to this. So if we fix two arbitrary elements, so it's the equivalent that we fix two systems in our class, and we consider the set of all point transformations between such systems. So it's some local diffeomorphism between this system. If we target arbitrary element coincide with source arbitrary element, so it's in fact will be maximal point symmetry pseudo group usually of this fixed system. And having pseudo group, I will talk, we can consider infinitesimal objects, which usually Lie algebras of vector fields. But we maybe need to consider pseudo algebras of vector fields. If we intersect all these groups, so we will produce kernel point symmetry group, which is mean common part of all point symmetry groups. And then, of course, it is completely natural notions about equivalence groupoid that this is a set of triples where we have source arbitrary element, target arbitrary elements, and corresponding point transformation on. Sometimes more general, we can also consider for single differential equations contact transformation. So it satisfies all axiom for groupoid, of course, and elements of equivalence groupoid we call admissible transformations here. And non-formally, this admissible transformation were considered by Kinson, Sophocleos, and Winternitz-Gazel. and they call this form preserving or allowed transformation, but they don't consider triples. They just consider point transformation, but between what was not clear completely. Yeah? And as counterpart of point symmetry groups on the level of groupoid, we have vertex corresponding groups, so again triples, and we also can consider fundamental groupoid of the class. It is union of all vertex group, and in fact we can assume that group classification problem is in fact problem of description of fundamental groupoid in some sense up to discrete transformations. So yes, usually we have small category, you have object our systems, or we can even assume that objects are arbitrary elements of the class because they define systems, and yeah, and arrows are local diffeomorphism. So, and usual terminology of groupoid, source, targets, and so on. So then how we can define equivalence group? It's more tricky definition. So I will define only usual equivalence group, yeah. So if we consider this projection through from the space, all entire space with x, u, derivative of u, and the arbitrary elements to the space, just x, u, or x and derivative of u, then usual equivalence group of the class is pseudo group of point transformation in this extended space, but it should be projectable to the space. So transformation of x and derivative of u should not depend on arbitrary elements. And this projection should be consistent with contact structure of the space. So in fact, for the next, for each next order, transformation should be just prolongation from lower level, yeah. And this transformation, of course, since it is equivalence group of the class, should map system from the class to again systems from the same class. If we have that arbitrary elements depends only on some lower order derivatives, that we can also lower order of the space in which this equivalence group acts, this P, because we need this dependence in theta. Yeah? So if we don't need this, so we can lower this order in this space. And if we have a group, so we can consider also action groupoid of this group. So we have corresponding triple. Yes, we have source arbitrary elements, then equivalence transformation, in fact, is projection to the space, and then transformed elements. Because when we have source, for any equivalence transformation, we can produce corresponding source. So, and kernel symmetry group of the class can be naturally embedded into usual equivalence group of the class, trivially just prolonging this transformation to arbitrary elements. So in fact, kernel symmetry transformation are equivalence transformation which does not transform arbitrary elements, roughly speaking. Yeah. So for normalized, I now will introduce notion of good classes of differential equations. So good here is equivalent to be normalized. So and the class LS is called normalized, or respectively semi-normalized. So in certain sense, so it's usual and generalized extended or generalized extended, yeah. If entire equivalence groupoid of the class coincide with action groupoid of the corresponding equivalence group. I defined only usual equivalence group, but there are also several other kinds of generalization for notion of equivalence group.
Sorry, Roman, a question. Yes, a question. These groupoids have any other additional structure? I mean, they are Lie groupoids, or they have any kind of...
No. It can have terrible structure, yeah. because like even somehow even symmetry groups can be pseudo groups, yeah, so they we have can have infinite dimensional Lie invariance algebra and so on. So this is why there is
it's
no
quite
finite
different.
dimensional structure, yeah, and
Yeah, I
they can be
understand.
very complicated. So this is why I don't know how where it is possible to get to somehow attach to this algebraic theory, yeah. But even usage of this language, yeah, and like notions, yeah, and approaches, so it's already very useful for solution of group
Yes.
quantification
I
problem.
see. Mhm.
Since like if we have this, so we already can so okay, I will continue here. So this is
Okay.
called the normalized class of differential equations here. But if anti-equivalence groupoid generated by action groupoid of the corresponding equivalence group and fundamental groupoid, or otherwise, each admissible transformation, roughly speaking, is the composition of equivalence transformation and point symmetry transformation from source element here. Then this class is called semi-normalized. Yeah. In both these cases here, arbitrary similar system from the class. Yeah. So similar means that there exists point transformation between them. Yeah. So then we can say definitely that this is related to equivalence transformation. So they are related transformation from equivalence group. And if we have, of course, normalized class is semi-normalized class, but we have much more good properties. For example, kernel equivalence group, then not just subgroup in each symmetry group, but we can guarantee that it is normal subgroup in each symmetry group, yeah? So we can factor out this common path somehow, okay? And what is more important, that of course it is easy consequence, but so that each symmetry group is a subgroup in the projection of equivalence group to the space of independent variables. Okay, and then what is algorithm in fact for carrying out group classification in the normalized class of differential equation? If we compute equivalence group and show normalization, we can again easily construct equivalence algebra from this group. Each Lie invariance group will contain a subalgebra in the projection of the equivalence group. So then we reduce the problem of group classification to the problem of classifying subalgebras in the equivalence algebra or in the projection of equivalence algebra to the space of independent and dependent variables. This is the main trick. Of course, if the algebra is infinite dimensional, especially, or even if it is finite dimensional but quite big dimension, yeah. So this is still a non-trivial problem, yeah. But this is already more or less algebraic problem. This like arrange all this approach, yeah, and allow due to like that all is transparent, yeah, somehow guarantees that at least the result should be correct up to misprints, yeah. The slide that, yeah, for each this group, yeah, we can consider the corresponding infinitesimal object, yeah, and so we have maximal Lie invariance algebra for single system, we have kernel algebra, we have equivalence algebras of various kind, but I'm not sure about this, where we can consider equivalence groupoid on this level, yeah, on infinitesimal level. So yeah, and then problem of group classification by classical formulation. We will work in this classical formulation, but in many cases it doesn't work. Yeah. So what we should construct? So we should construct equivalence group. We should find kernel algebra, and then after that we should construct this list of inequivalent extension with respect to equivalence group. Yeah, of all possible extension of this kernel algebra. Okay, and this is already more specified. Of course, equivalences may be different, yeah, but two basic equivalence are equivalence with respect to equivalence group is and the equivalence with respect to the corresponding equivalence groupoid, but it's in fact equivalence with respect to all diffeomorphism which acts in this between elements in this. Yeah, and if class is not too good, yeah, then this is a big problem. Which equivalence we need to take, or maybe we need some take intermediate situation, or split class into subclasses and then classify each subclass separately with respect to the corresponding equivalence group, because that equivalence group may be wider or narrower and so on. This way, yeah, it's a very big problem when class is not too good. To do this, yeah, but now we already start with the class of differential equations in question. Yeah, so we consider such class of equation in light cone so-called variables, so where we have just mixed derivatives, not utt minus uxx, but we write in this form of equation. So we at once exclude the linear equations from this class. So they, in fact, their classification is well known, and we also show that linear and nonlinear equation cannot be mixed within this class. For example, if we consider more general class where we have here also derivatives ux and uy, so this is not already the case. But for this class, it is natural to exclude linear equation. Of course, the most famous subclass in this class is the case where nonlinearity does not depend on T and X. And there are several famous equations in this class. I already mentioned Liouville equation, yeah, but none of this equation can be singled out by just using classical Lie-symmetry, so it's already rather on the level of generalized symmetry, so it can be singled out. So, and then we follow our algorithm and systematically compute all what we need for our purpose, but very important role in this consideration plays the Lie theorem on realization of the algebra by vector fields on the line. Yeah, and so it is well known that there are, okay, if we exclude 0, so there are 3 in equivalent regular realization here local by vector fields. So they are very simple. It's just shifts and corresponding scaling. Here, the shift scaling and corresponding conformal transformation. So it's very nice that on the line here the number is so small. On the plane it is a much bigger, of course, number, and not to mention about space, about 3 variables, as we already discussed it here. And this theorem will work in twofold way, not only with respect to variable t, but also with respect to variable x. That's why it is especially efficient here. But we still need to be prepared for this application. Yeah. So it is possible to check that any contact admissible transformation within our class of Klein-Gordon, generalized Klein-Gordon equation, it just first order prolongation of point admissible transformation. So it is enough to consider only point transformations here. And this is a very important lemma which says that our class is very good. So it is normalized in the usual sense with respect to both point and contact transformation, of course, due to this lemma. And which means that point and contact equivalence groupoid coincide with the action groupoids of the point or equivalence group or its first prolongation. Yeah, and the point equivalence group is of course it is not group but pseudo group, because sometimes I consists of the in fact generated by transformation of this form and one more discrete equivalence transformation, just permutation of variables. It's really discrete transformation, because there are also mistakes in literature, a number of mistakes with identification discrete transformation. What transformation are discrete and what are continuous? Yeah, that's really discrete transformation. Okay, So here two arbitrary function of t and x, also arbitrary function of two variable and arbitrary constant. This is just usual non-degeneracy condition for transformation to be regular. So, and this is here already visible that we will have two variables here. So because transformation t depends only on t and transformation x depends only on x, this is why Lie theorem is relevant. Yes, strictly relevant. Okay, so then we can describe the entire set, of course, discrete equivalence transformation in this class. So it is the group D4 multiplied by Z2, diagonal group here, and it's usual Z2 group, two element. Yeah, and we also prove that there is no transformation between equations where fu is not zero and fu is zero, and that's why we can exclude. Sorry. Yeah, we can exclude. It is in fact second derivative. So, but we can exclude linear equation from this class. Since we have description of equivalence group, we can also easily derive from it description of equivalence algebra. So we have such vector fields in this equivalence algebra. And for Lie-symmetry, we also have this similar form. So you see it is like analogy between them because it is due to normalization property. Yeah, all symmetries should be contained in the projection of the equivalence group. Yeah. And so in more detail, so in fact, we can say that if we consider linear span of all points, linear invariant algebras of equation from our class, then we will produce such set of vector fields, which is, or in other words, it is spanned by such vector fields here. It seems to me. Okay, and so any invariant algebra is subalgebra of this algebra, but not all subalgebras are appropriate. So that they are maximally invariant algebra for some equation from our class. So I introduce this notion for subalgebra being appropriate, that it coincides with some maximal invariant algebra of an equation for some f from our class. And since not all subalgebras are appropriate, we can classify only appropriate subalgebras, and the amount, of course, much less, yeah, because since we work with infinite dimensional algebras, then the problem of classification of all subalgebras and its algebras may be not solvable. Yeah, but we identify appropriate subalgebras, and they really have quite restrictive properties. So amount of subalgebras which are appropriate really is very, very small in comparison with all subalgebras in this big algebra. Yeah. So, and what are properties? So the first property is that intersection of maximal invariant algebra with this linear span, so with these two vector fields, yeah, is zero. So this means that for some symmetry, we necessarily need to have such vector fields in each Lie-symmetry vector field as a path. Okay, then Lie invariant algebra is infinite dimensional if and only if equation from our class is equivalent to the Liouville equation. So only Liouville equation in this class has infinite dimensional invariant algebra up to equivalence. And then for all other equation, we have finite dimensional algebra. And moreover, we can estimate that dimension of this algebra is not greater than 4. So we need to classify only subalgebras up to dimension 4. And moreover, due to theorem, then we have that if we will make projection of these elements to t direction, yeah, that we will have only such term, which means that but projection should be then again Lie algebra and infinite dimensional. But since where does not exist for dimensional algebra, so dimension of the projection can be not greater than 3. And the same with direction x. So now we strongly restricted the set of subalgebras, yeah, in which we will try to find the appropriate subalgebras. And then we can start to classify all such subalgebras and check where they are appropriate. And this will give complete solution of this problem. So the classification list. So this is, in general case, we have only zero algebra, yeah, no extension. And we can see how these two kinds of realizations in t variable, in x variable, they intersect, they interact to each other. Yeah. So, for example, here we have realization dt, yeah, one-dimensional, and zero realization with respect to x. Yeah. Here we have some of this one-dimensional realization. They are not independent. We have some. Here it's the additional extension to this. Here this is additional extension, like additional sum onto this. It's variation extension here. Here we have one-dimensional realization by Lie independently with respect to x, t, and x. Yeah. Here the same. Here we already have this sum of one-dimensional realization and sum of sorry, because it is two-dimensional realization, but we have somehow sum. Yeah, these elements we should add. Yeah. This is another composition. So we, in fact, it is one-dimensional realization here with respect to x, and we would make here dx, but more convenient to present this as a function. This is why we have here x dx here. So here we already have one-dimensional realizations independently, and like in this for two-dimensional parts they combine, yeah, somehow. And what is interesting observation that because we can have three-dimensional projection with respect to t and three-dimensional projection with respect to x, but in this class they are possible only together. So we cannot make separately realization of SL2 in t variable and realization in x variable. So, but yeah, it's one of the possible inequivalent realization of the algebra SL2 by vector fields. So, and this is the only one. Of course, not it is not related to Liouville equation because here algebra is infinite dimensional. They definitely contain such vector field as well. So up to excluding Liouville equation, the only one case exists in this class where we have SL2 algebra. Yeah. And was the list is quite concise. Yeah. And moreover, we checked it in several different ways. Yeah. So it's quite trustable classification here. Moreover, we construct here Hasse diagram, so successive extensions. Yeah, and we also consider this like construct this classification in this way. So we know all relations, so that like of course the zero case is minimal and all other cases are extension for it. But for example, this case has these three successors. Yeah, so it is additional extension for these two cases. Like for example, we have this case, which is additional extension for lower cases here, but not for this level here for n equal to 3. So we have only one. It's also related to this SL2, so SL2 cannot be further extended here. So, and of course, singular case is the case of Liouville equation where algebra is infinite dimension. Yes, please.
Is there any manner or any characterization of these maximal cases? I mean, the case 11, case 12p or something like that. Could you comment how you know that you will reach such a case, the maximal case that is not containing anything else?
Okay, to check that there are no equivalences and that they are really inequivalent, yeah, and order it in such way, introduce a big tuple of invariant characteristics, yeah, which algebraic. So related to algebra, different dimensions of intersections, projections, dimension of algebra itself, and so on. And that's why we can guarantee that these cases are not related only in this way as it is mapped here, yeah. And this is really like the case of maximal dimensions. It's only one case, yeah, in this way. And we also study possibility of limit transitions between these cases also, yeah. So we also describe limit transitions, yeah.
Okay.
It's also possible.
Great.
So thank you very much for your attention.
Thank you, Roman, Professor Popovych, for your nice talk. Thank you. So,
Thank you for attention.
Is there any question, remark? Well, truly speaking, I have several ones. On the chat, okay, I can send you afterwards, but there are several references to the description of PDEs by means of relative algebraics. One is by Rui Loya and Wilde Smilde. It's from Holland, I think. And another one, the second one is about symmetries and Pfaffian systems. So it could be close to what you are doing here. So this is quite new. So it looks, as I told you, I told you it's quite promising. And one of the things is written, and one is absolutely what is written in the chat. The relative algebraic and Pfaffian fibration are two frameworks recently developed to study geometric extraction PDEs with symmetries. In the work, essentially, we describe them and they establish symmetries for them by means of relative algebraics and Pfaffian groupoid. So, no, I don't know. Maybe it could be interesting. It's also applied to describing the group symmetries, and I think that it was pretty much well. I don't know if it is interesting or not, but it's nice. This is one thing. The second thing is, could you please go back to your slide about the Lie algebras of vector fields of the real line? The result by Lie that every okay, this one. Okay. These, yes, maybe you know it because it's difficult to give all the remarks, but realization of finite D. What does it mean finite D Lie algebra? Dimension.
Finite dimension.
One dimension.
Yeah.
One dimension. Yeah. Okay. So look, for instance, these Lie algebras are for vector fields at a generic point. I mean, if you pick up, for example, a vector field, partial t, and you multiply it by means of a smooth function that is not analytic, the typical one, to minus 1 divided by t squared, yeah? There will be no diffeomorphism mapping this vector field or the Lie algebra, okay, to any of these one on an open subspace containing zero. Because when you change the variables, the coefficient you have, the order of the first non-zero element is geometric invariant. And here you see in this Lie algebra elements are up to T2, yeah? And when you have an analytic, you know they will be to infinity. So it's just a remark because the smooth category does not work properly with these vector fields around a certain particular point. And yes, I found problems with, for example, studying stability and things like that. This is one thing. The other thing is, well, this is a remark. A question is, have you applied this formalize to other PDEs apart from Klein-Gordon equations? have you tried to study more problems than this one that you presented today?
No. We study a lot. We classify, in fact, a lot of classes of differential equation. We have
Yeah.
classes of Schrödinger equation. Yeah. And even when we classify Schrödinger equation, this theorem is important, but only with respect to t, yes?
Yeah, I
We
see.
also have the same effect that like projections of entire algebra, Lie invariant algebra to the t direction cannot be greater than dimension 3, and this is in fact an equivalent realization for this. So
It's a hard problem indeed. Interesting but hard.
yeah, but of course, for example, we classify with my students some classes of Schrödinger equation which are not even normalized, yeah, and then we classify with respect to equivalence group and its extend cases more and more, yeah. But I don't know, it's like 50 cases, I don't know. It's already a different order, but again, it's all very transparent, yeah, and that's why it is possible to check, yeah. And first we even write classification list just without the proof, just when we already prepared all, we write it by intuition, and then we make this proper classification and found like that we forgot two cases, yeah, when we just write without proof, yeah. So
Yeah,
it's why it is necessary to correct intuition sometimes, yeah.
But I read your paper and I like because of what you said. That many people they just use brute force. Yeah, they just go for the thing, and there are no much. The good thing is that your algorithm and you methods that you have additional tools to check whether everything fits or not. So it was kind of interesting. Anyhow, the problem is still hard, but it's a step, an interesting step forward. Okay, so is there any other question, remark, comment?
Only one more remark, because
Yeah, sure.
about your first your first part of your not question but remark. So that were also classifications of realization in the neighborhood of a singular point. Yeah. I don't remember. So it seems to me Dreisman tried to do this, yeah, and also maybe Lichagin and Kruglikov, I'm not sure, yeah, but like these peoples, they try to classify realization of later as a globally than locally, because this is local realization, yeah.
Yeah,
Local
around
realization.
singular points. Yeah.
Yeah.
I mean, this is something. If I can't tell you, when I several years ago, I meet several times Winterny, yeah, and look to the Olbers, Cameron, and Artemius classification on the plate, and see, he always told me that there is something missing there. There are some cases and things, and that. I asked him, "Oh, okay, which cases?" I said, "Oh, I will work for you. I will tell you one day." And time passed by. He didn't tell me. He just said, "Oh, I think that these cases are nothing special." Then after this many years, I tried to. I found that there are several assumptions, at least that locally at a general point and things like that, that they don't fit in this scheme. I mean, I don't mean that Olberg, Camden, and Temius is wrong. Well, the only I say is that there are many assumptions or several assumptions that they are not explicitly commented after the word. People do things and then I'm missing. But it's quite difficult to say everything technically correct. This is what I mean. And in my case, I was interested in stability points because one of the students, he has finished his PhD here, so he's not a student anymore. But Bartos was working about the stability, and one of the things I did was to look for this classification with singular points. As you said, there are several guys working on the topic. I don't remember their names. The result I told you about the one vector field that can be mapped by means of the theorem is that the coefficient the first non-zero coefficient that Taylor expansion is an invariant, a geometric invariant. I found it by myself, but then it turned out that someone found it before. But I don't remember his name. It's not, I cannot say that it's mine. And there are several more. If you know about it, something collecting this thing, even in the simplest case, I will be very thankful if you can send me a reference, because that's something that is, even on the real line, I have a work with this result by Lie doing with singularities and with several exceptions. It would be nice to do it in such a manner that I'm sure that I didn't skip any case by other guys. So if you know anything,
I will try to find Javier.
Yeah, if you have,
because I don't remember precisely. I will try to find. It was a long time ago. I saw this.
Roman, it's not a matter of a couple of days. If you find it, okay. If not, don't worry. It's okay. We'll deal with it.
Yeah, and
But,
my one more comment about Pavel Vinternitz, because unfortunately he is not already with us. But so his solutions of group classification for classes of differential equation in can be included in more or less trustable classification amount of more or less trustable classification, as well as his classification jointly with Patera-Zesenhaus classification of subalgebras in the algebras.
Yeah, sure.
And my student recently reclassified this subalgebras in SL3 algebra over real and complex field, and several people did this, and they found in Winternitz classification 2000, it seems to me one, he classified only a few weaknesses, so it was not so terrible as in other classification again. And especially take into account that he classified the subalgebra single, without coffers, nobody checked it, in fact, and so on. So it's really incredible results.
I know events. I remember that there is. I work on. I discussed this topic with him. I know in 2015, 10 years ago, 11 years ago, and he proposed me several things, and he said, "I have no idea how to finish the some classifications." And the first thing is that he had a fantastic mind to find shortcuts to do the classification. I mean, he could imagine or whatever how to do it to transform. The bad thing is that there is, in many cases, there is not an algorithm or something like to do it. That many of the things he did for me, they were magic. I was something like, I asked him, he said, I found this equivalence, I found this transformation, and it worked it out, and I did the job. I don't know why it was this and not another things. But it was quite a good thing. But it's not finished. There are several cases, but he was when I talked to him, he had no faith on finishing these classifications, but he did a real huge work in that. Okay, so any other thing, or we can leave our speaker? So Professor Popovych, thank you very much. It's been a pleasure, and I hope I will see you again soon, someplace in Opava or maybe in Warsaw. Who knows?
Thank you very much. I will. I hope I will participate in your seminar, definitely. Okay.
Yeah, I hope so. It's been a pleasure, really. Thank you. Okay, and see you everyone next week. We have next week. 1 second. I have to remember. We have Galma. Next week we have Ruben Izquierdo from ISMAT, the gradient Jacobi bracket in dissipative field theory. So see you in a week. Thank you.